Hi, I'm Carl Salter, chemistry professor at Moravian College. Today we're going to show you a demonstration involving acid-base extraction. The kind of typical laboratory procedure you'd do in the organic lab using one of these separatory funnels. The demonstration that we're going to do was actually presented in the Journal of Chemical Education back in 1993. The author was Ross Kelly of Boston College. And as you can see, it's a very colorful demonstration, which is great because you can see the chemical compound moving between the two layers as you do the chemistry. We're going to show you the chemistry of dichloroindophenol in test tubes before we actually do it for you in the separatory funnel. Here's the way that dichloroindophenol comes to us from the manufacturer. It's actually given to us as the sodium salt, so it's already fairly water soluble as a result of that. This is what it looks like. It's a kind of a dark blue-green solid. 25 milligrams of this material in 50 milliliters of water will give you this dark royal blue solution. You can add a little bit of sodium hydroxide to help it go into solution. Now this solution is so dark that I've actually taken it and diluted a little bit with water so that you can appreciate just how dense the blue color is for this compound. Now I'm going to split it between these two test tubes. So we've now split the solution between these two test tubes, and we're going to take one of them and we're going to add hydrochloric acid to it so that you can see the difference in color. And you can see now that we're developing a red color for the neutral species of dichloroindophenol. Okay, now the last thing that we want to show you is what happens when we take the base form and the acid form and add chloroform to it. So I'm now going to add just a tiny amount of chloroform, which will go down to the bottom of the test tube. Shake it up. And you can now see that the base form is not soluble in chloroform, but the acid form is. And now the red color is migrating to the chloroform layer in the bottom of the test tube. And it's this change that we're going to take advantage of in the separatory funnel. So the molecule that gives us all this color is this molecule, dichloroindophenol. Now it has a quinoline ring system here which gives it some redox chemistry, but we're not really interested in that today. We're interested in its acid-base chemistry. For that, we have this phenol group, and that proton is mildly acidic. So if we were to take this compound and react it with sodium hydroxide, we would pull off the proton, and now the sodium ion would be the counter ion for the molecule. Of course, we can also reverse that process with strong acid. If we have the anion, we can take it and react it with hydrochloric acid, put the proton back on the phenolate ion, and recover the phenyl group. Now, the pKa of dichlorophenol, which is roughly half the molecule, is about 7. So that's probably a pretty good model for the pKa of our compound. So if we can get the pH to about 8, it's going to be in the phenolate form. If we get the pH below 6, it's going to be in the acid form. Now the really nice thing about all this is, attendant with these changes are color changes. The form of this molecule is red, the basic form of the molecule is blue. So Rachel will do the demonstration for us. She's already prepared the SEP funnel with 100 milliliters of deionized water and 50 milliliters of chloroform. The next thing that's going to happen is we're going to add the solution of dichloroindophenol to the separatory funnel. And she'll do that, and then we'll start the demonstration. So just a few milliliters of dichlorophenol, a very dilute solution in fact, 25 milligrams in 50 milliliters of water with just a touch of sodium hydroxide to make sure that it goes into solution. Notice that that's going into the upper layer, which is the water layer. So she's capped the separatory funnel, and now we're going to stir it up a little bit. It's always a good idea to vent the SEP funnel a little bit when you're mixing the two liquids together, because the vapor pressure can change. Now we'll let the layers separate, and we can see that the blue color is still in the upper layer, the water layer. So we currently have the sodium salt of dichloroindophenol, and now we're going to add hydrochloric acid to put a proton back on the phenolate ion. Rachel's going to stir the upper layer so that you can see that the upper layer is now going to change to the characteristic red color of the neutral compound. Now we're going to shake it up. And you can see that the color is changing as the compound goes into the chloroform layer. And now as the two layers separate, you can see that the dichloroindophenol has moved down into the chloroform layer. Now we're going to reverse that by adding strong base. Sodium hydroxide is now going to go into the separatory funnel. Rachel's going to stir the upper layer, and you can see that it's what little dichloroindophenol is in the water layer is now turning blue because it's reacting with the sodium hydroxide. Now we'll mix both layers together. If we added enough sodium hydroxide to neutralize the hydrochloric acid, then there'll be sodium hydroxide left over, and now we will convert the dichloroindophenol back into the anion, which is more soluble in water. And sure enough, we now have a blue layer on top, just like when we started. We can repeat this as many times as we want. We're going to repeat it again, and this time we're going to measure the pH at each step. So first, we'll add hydrochloric acid, make the neutral compound, which will be more soluble in chloroform. And the red color on the pH paper tells us that it's now strongly acid in the water layer. And we again see the characteristic color of neutral dichloroindophenol when it's in chloroform. Now back to sodium hydroxide. Rachel will now stir that in and test the pH of the aqueous layer on top. And now we can see that it's darkly colored blue, which indicates that the solution is now strongly basic. And now we mix the two layers together again. The red color's gone. And the anion form of the molecule is now dissolved in the upper layer, the water layer.
Now that we've looked at one acid-base extraction in detail, let's see if we can create a general strategy for exploring a variety of such systems. We'll start with dichloroindophenol, but we'll switch the solvents to water and ethyl acetate. First, we'll fill a test tube with about 8 to 10 milliliters of each solvent. Then we add our indicator solution drop by drop until we get a color in at least one layer. We want a color we can see, but we don't want the color to be so intense that we can't see through the test tubes. We'll keep that test tube as our control. Then we make up 2 more test tubes the same way, and we add the same number of drops of indicator to those tubes. Now we're ready to see what happens when we add strong acid or strong base. I used 0.5 molar hydrochloric acid and 0.5 molar sodium hydroxide. On the left, you see the control test tube containing the mixture of dichloroindophenol in water and ethyl acetate. Then the mixture with added acid. And on the right is the mixture with added base. You probably recognize the colors for dichloroindophenol. We have the red color for the neutral phenol and the blue color for the phenolate anion. But now the colors have switched layers. That's because the water layer is on bottom and the ethyl acetate layer is on top, because ethyl acetate is less dense than water. Of course, the most famous acid-base indicator is phenolphthalein. When we make our control test tube, we don't get any color, which is a bit disconcerting. But if you've used phenolphthalein, you know that 2 or 3 drops is enough for a titration, so 2 or 3 drops should be enough for a test tube. When we add hydrochloric acid, we don't get any color, but sure enough, when we add sodium hydroxide, we get pink. And that pink is in the water layer. That's because phenolphthalein also has phenol groups, just like dichloroindophenol. The sodium hydroxide removes protons from the phenol groups, giving us an anion which prefers the water layer. Perhaps there's a way we can show that the phenolphthalein in the acid test tube is actually on top in the ethyl acetate layer. We'll leave that for you to discuss with your classmates. An important acid-base indicator with some structural similarities to phenolphthalein is bromocresol green. You can see in the control that we definitely get a green color in the water layer. Now, if we add hydrochloric acid, we get yellow, and perhaps we get more yellow in the ethyl acetate layer on top. Adding sodium hydroxide gives us a blue water layer. Once again, this is an indicator with phenol groups that will be deprotonated by base. A very different acid-base indicator is neutral red. Neutral red has an amine group that can be protonated to form a cation, and so it is water-soluble upon the addition of acid. We see a strong magenta color in the water layer when we add hydrochloric acid. On the other hand, sodium hydroxide will deprotonate the ammonium ion, giving us a neutral compound that prefers to be in the ethyl acetate layer. Thus, we see a yellow ethyl acetate layer in the last test tube. Acid-base extractions are a workhorse technique in the organic lab. I hope the use of acid-base indicators has helped you understand what's going on during an extraction. There are many acid-base indicators that could be explored by this method. There are also other organic solvents, such as octanol, ether, and dichloromethane, that can be used with water for an extraction. Perhaps you'll be able to explore some of these other systems yourself. Good luck and enjoy.